Okay, so moving on with our Platonic solids, and I am back at school doing this video, so I do have the other two Platonic solids with me. So this is the icosahedron, sometimes it's called an icosahedron, but it's again made of equilateral triangles. There are 20 of them, so there are actually 5 that kind of make this top here, and then there are 5 that make the bottom, and then this middle part here is just like a band of them around. So there are 20 in there. So it's another Platonic solid. And then finally, the other one is a dodecahedron. And it's a little bit hard to see on here because it's so big with our pentagons that we have are just big, but you can see that 3 pentagons come together at each vertex, and there are 12 of them all together. Okay. Alright, so let's again keep looking at the math behind how many of these and which of these shapes can be possible. Okay, so what if we want pentagons, which we actually just saw, right? So we want 3 pentagons to come together at each vertex. Sum of the interior angles of each face. Well, a pentagon has 5 sides, so n is going to equal 5. And so n minus 2 times 180 is 5 minus 2 times 180, or 3 times 180, which would be 540 degrees. That's the total, the sum of the interior angles of that pentagon. So a pentagon has 5 sides. That means it has 5 angles because it's regular. They are each the same, so we're going to take 540 degrees divided by those 5 angles. So each angle is going to be 108 degrees. And then when I have those 3 pentagons around a vertex, okay, so if we can kind of see here, oh, it's tough to see. This yellow, this green, and this blue, each of these is contributing 108 degrees. So 3 times 108 is going to be 324. So again, picture like I was doing before, if that was flat before we folded it into the shape, yes, there's enough space there to be able to fold it into a shape and still have some space there. So this is the dodecahedron. Okay, what if we wanted to have hexagons instead, right? So a hexagon is going to have 6 sides. It's a regular hexagon, so they're all the same. So n is going to be 6. 6 minus 2, n minus 2 times 180. So 4 times 180 is 720. So all the sides of the hexagon make 720. And then I take 720 divided by 6 angles, because that's how many angles a hexagon has. So each angle is going to be 120 degrees. So if I put 3 of those hexagons together, times 120 degrees, this is going to equal 360 degrees. So this is similar to when I tried to put 4 of the squares together and it equaled 360, and there's not space to then fold it down and to make it into a shape, right? So similarly, if I have hexagons, so then I'm going to have another hexagon here and another hexagon here, right? This uses up all of that 360 degrees. I can't fold it down. So this shape is not possible. So we cannot have a shape where a Platonic solid where it's only made of hexagons. Okay, I can't have fewer than this hexagons because that won't make a shape, but I can't have 3 hexagons. So far I can have 3 triangles at each vertex, I can have 3 squares, I can have 3 pentagons. And this gave us 3 of our different Platonic solids. Okay, so let's keep going. Now, what if I want to have 4 triangles come together at each vertex? So this column here is the sum of the angles in the shape in each face. This is each angle in the face. And this is the sum at each vertex. So we already know that if we have an equilateral triangle, it's going to have a sum of 180, and each angle in that triangle is going to be 60 degrees. We know that from the other side. Now we want 4 triangles at that vertex times 60 degrees each is going to be 240 degrees. So is this shape possible? Yes or no? And then the name. Well, 240 degrees, I still have some space there where I can fold it down and make it into a shape. So let me get out my, let's see, my little shape here. So here's tetrahedron. So if I want 4 of these triangles coming together at a vertex, I can do that. I can see that right here. Because it's 240 degrees, that leaves a little space where I can fold it, and then that is going to be this shape. And I had taken this guy out, so let me put him back, and then it looks like we're missing one other still, which I will put in a minute, but this is going to be with this here. This is going to be our octahedron. So yes, it's possible. It is called an octahedron. Okay, how about 4 squares at each face? Well, we know that a square has a sum of 360 degrees. Each angle is 90 degrees. Now what if I want to put 4 of those 90-degree squares together? And we already saw this, right? I had showed you earlier what happens if I try to put 4 squares together. And we said that in that case, you know, it fills up this space here, and then there's nowhere, I don't have any freedom to bend this into a shape. So it did not work because this equals 360 degrees. So there's no space, it's not possible. Okay, what if I want 4 pentagons? So we know 3 pentagons can come together. How about 4 pentagons? Well, we see from over here that each pentagon has a sum of 540 and each angle has a sum of 108. So in a pentagon, the interior angles are 540. That means each angle is 108 degrees. So what if for a regular pentagon? So what if I put 4 of those together? Well, what I get there is 432 degrees. So again, way too much. If I tried to put 4 pentagons together, I couldn't even fit a 4th one in, okay? The 3 pentagons give me a little space, but that 4th one, there's not even space. It would have to overlap. Right? And finally, what if I want to put 5 triangles around a vertex? So each triangle has 180 degrees. Each angle is 60. If I have 5 times that 60, that's what I'm putting around a vertex, that's only 300 degrees. I still have space to be able to fold that into a shape. So yes, this is possible. And this is what we call an icosahedron. So that is this guy right here. Okay, we can see that we have 5 triangles coming together at a vertex. I don't want to take this apart to show you because this is really hard to put back together. But you could picture that there must be a little bit of space and then it folds down and connects. So the 5 Platonic solids are a tetrahedron, And this is made up of 4 equilateral triangles. A cube, which is made up of 6 squares. An octahedron, which is made up of 8 equilateral triangles. A dodecahedron, which is made of 12 regular pentagons, and an icosahedron, which is made of 20 equilateral triangles. Okay. Now, there are other shapes. If you think of like a soccer ball, right? A soccer ball is alternating hexagons and pentagons, and so that's why that works the way it does. But we just cannot make any other shapes that are made only of a single shape on each face that are regular. Okay. Why can't we have any other Platonic solids? Well, we could see here that these are the only solids that don't have too many degrees at each vertex. Okay, that's not the most formal way, but we can see that's why. And we can see also that if we tried to put 6 triangles together, right? We didn't get to that here, but if we try to do 6 triangles, they'll fill up that whole circle, and again, I can't bend it to make a shape. Okay, so you do not have to be able to recreate this whole chart. I want you to know what Platonic solids are. They're shapes that have every face the same, and every face is a regular polygon. The same number of faces meet at each vertex. Okay, and just understand that you can't make an infinite number of them. There are only 5 of them. Those 3, and then this one, and others are not possible because of the way those shapes come together at a vertex. All right, thank you for watching the video, and I will see you next time.